Test check. Okay, great. Okay. Okay. Yes.
I was thinking that maybe, I'm not sure if that's a good idea, but maybe we could solve a single problem from the test that pinpoints both the struggles. Because we have this prefix function that uses 3 instead of 2, 3 equations instead of 2, so it doesn't follow the standard. And we also have this as pattern there.
Okay, just let me see.
Checks is the first, is prefix of the second, so in the case it's true because they're equal. In the second is Genesis block the first no, so it's not like this one is not bigger than this one, so it's false. In this final case, checks recursively, but before it's that if it's recursive or if they are equal, so it's like the first case.
Okay.
Makes sense?
Yes, it does.
And we do 3 equations, this, and also prefix of like this, so it's all 3.
Okay, right. Good.
Yeah?
Right. I must just get the. Yeah, okay, that's fine.
I can leave here though.
Yeah, maybe.
Yeah.
Okay, great. Thank you. I'll do that. something is wrong there, but that's fine. We can figure that out later.
Maybe if the container was already running, you don't have any VS Code open.
No, I don't think so, but it doesn't matter.
Okay. I don't know how to.
No, it's fine. Thank you. Okay, let's start with today's lecture, which is on higher order functions. But before we start, I just wanted to say one thing I forgot yesterday and one thing that came up during looking at some of your solutions to the exercises. Let me just start with what I forgot yesterday. Why is this not going away? Now, okay. Right, and we were talking about type classes, and I just need some example. It doesn't matter, but maybe I can do. Okay, chain. So we in the first lecture we had this chain TXS. And there were two constructors: Genesis block or block with I don't know what it was called. So it had this and then the newest block. Right. So the first, I could derive equality as we learned yesterday by just deriving eq. But let's say I would, for whatever reason, want to do this by hand. I want to define an instance of chain TXS, eq chain TXS, where? So I need to implement this equals equals. And I told you in the very beginning that it's considered best practice in Haskell to have type signatures for top level definitions. So I would like that here as well, of course. So what's the type of equals equals in this case? Well, it takes two chains and produces a Boolean. Right, and if I do this, maybe it's automatic? No, it doesn't. Okay.
No, but maybe if you
compile
undefined, you will.
Yeah. Let me just put undefined there for a second. Right, now I get an error, and it says illegal type signature in instance declaration. So for whatever weird historical reason, even though you are encouraged to always provide signatures for your top level definitions, you are not allowed to in instance declarations like this. But there is an extension for that, and it's also suggested here. Use instance 6 to allow that. So we can just, here it's a quick fix. So it adds this language pragma here. And with this, then this compiles. So I think it's useful to always activate that, because often, here it's simple, the type signature, maybe you wouldn't need it, but there are more complicated cases where it really helps to have that. And now I could implement it. It's easy to implement in this case, although it's wrong. I need equality on, so we'll see. So how would we implement this? So Genesis block equals Genesis block. And in that block case, if we have, x's and x, so when are those equal? Well, recursively, the prefix must be equal. So block xs equals block y's. But in addition to that, we also need that the last block is equal. So x equals y, and then of course I get an error because I'm applying equality for, oh yeah, and okay, I also get a warning that it's not complete because there are two more cases, genesis block and block and genesis block, but those are of course not equal. But now I still get an error, obviously, because I am comparing two values of type TXS for equality, but I don't know anything about the type TXS. So as we learned yesterday, I can fix that by requiring here that you can compare TXS for equality. And now I still get something. Oh yeah. All right. And this is, sorry, I made a mistake. I mean, what I want is, of course, the XS. Sorry. Then I could actually have fitted it into one line. Okay. Right. So that's that, instance 6. And now for the remarks to the exercises, let me just implement one. So there is one of the exercises is to implement is prefix of, which takes two chains and returns a Boolean. So the idea is it should check whether this chain is a prefix of that chain. So it may be shorter, but if you put them one after below the other, then the one may be, this one may be shorter, but where they overlap, they should have the same blocks. And how can we check that? One case is easy if both are the genesis block. Then it's true. Okay, and now right. This is also an easy case. So if the one is not the genesis block, the first one, and the other one is, then it's false, because then the first one is longer than the other one, so it can't be a prefix. Now the interesting case is that the first one we don't really care what it is, but the second one is not the genesis block. So let me align better. Right. So, and there are two cases now. So how can this be a prefix? And we recursively can use is prefix of for C and XS. So if C is already a prefix of XS, then that's fine. Then it's also a prefix of the longer one. So that's one case. So in this case, I maybe really need two lines. So is prefix of CXS. Right, but there's a second case, namely that they are equal. Then they could also be, then it also counts as prefix. So I want to write, or I could write C equals block XSX, which is fine and it's correct, but it's inefficient a little bit. In two ways, both to write the code and also when you execute it. To write the code because I have to duplicate this thing here. And it's also inefficient at runtime because you basically have this argument, the second one, you pattern match, so you destructure it into its parts, XS and X. And then in this here, then you reassemble it. So you take a value, take it apart, and then put it together again, even though you have the original one that you want to use here already. And for that, there's something we haven't seen yet, so-called as patterns. I mean, this is a pattern. This is on the left-hand side of an equal sign. And we can give names to patterns and then use them. So in this case, I could call this D. And the syntax is, so it's D, I mean, name at the pattern. So this now gives this whole thing, in the parentheses, the name D. And now I can reuse that here, this D. And now we see we don't actually need the X. So I can replace that with an underscore. And right, so that's as patterns, so that can sometimes be useful. Another example was yesterday. We had this all equals, yeah, want to say something else about this, but let's just revisit this all equals. So if we have A and list of A to bool, we had this example function that checks that all elements of the list are equal. So we said if it's the empty list, that's true. If it's a singleton list, it's also true. And if it contains at least 2 elements, then we must check that x equals y, and recursively that all equals y zs. And here we have the, again, that's how I wrote it yesterday, because I don't want to complicate matters, but here we have the same problem again. So here we already have this list, we deconstruct it to make, and then we construct it again here. So that's slightly inefficient, and we like duplicate ourselves. So alternatively, I could again use an as pattern, for example, call this tail access. And then use this here. And then I wouldn't even need to name this thing here. So that's slightly more efficient. And also compact, more compact to write. So this, again, this is an as pattern. It gives the name XS to this part after the at. And then I can reuse it on the right-hand side. Okay, and the last thing I wanted to say here, that you see that you're not all, I mean, we learned the standard design pattern for functions. If a function has 2 constructors, you have 2 equations. So in this case, we have 2 arguments of type chain. So we would expect 4 equations, but you don't always need all 4. In this case, I only needed 3 because those 2 behave exactly the same in this case. It doesn't matter whether the C is a Genesis block or not. Just so it's not always that you need all the cases. And also sometimes if you can have nested patterns that you, but we saw examples of that as well yesterday. Was that everything?
Yes, maybe it will be more readable if you use is prefix of is an infix function while using it. Because it reads like C is
right, I forgot, sorry.
So it reads.
Yes, I mean the naming is made in a way that suggests it's better to use this as an infix, that's true. So what Robertino is saying, I could here use this as infix, as we learned in the first lecture, that by using backticks you can turn a normal prefix function into infix notation. And this, I mean it's now 2 characters longer than before, but it reads nicer. Because now it says C is prefix of XS, and the name is chosen in a way so that it's, I mean, grammatically correct. So yeah, that's good. Are there any questions to that, or otherwise we start with the higher order functions? Okay. So, I mean, we said several times now, I think at least twice already, what a higher order function is. So one that takes, it's a function that takes as an argument a function or as a result a function. And we also, yesterday, this is a duplication of some of the slides we saw before, that currying is, I mean, strictly speaking, if you go by this definition, then every Haskell function with more than one argument is a higher order function. Because a curried function, I mean, a function of two arguments like lm, strictly speaking, is a function of one argument that returns a function of another argument. And we saw these two already, filter and map, and they are both higher order functions because they take functions as arguments. So filter takes a predicate and then only keeps the elements of the list that satisfy the predicate, and map takes a function from A to B and applies it to every element of the list of A's to get the list of B's. Right. And now we learn a new one, and that's just called dot. So it's an operator. So from the shortness, you can already, see that it's probably very commonly used. And here we want to go through the exercise to train your type inferring skills to basically figure out the type together. But let me first hide it. Okay. So if we were to define that ourselves, right, so that's the definition. And now we can from so f dot g applied to x is f of g of x. So now we can try to figure out what the signature of dot is. So first of all, it takes three arguments, f, g, and x. So it's something like this. Right. So we don't really know anything about x. So let's just give that some type parameter. So x is of type A now. So now here we see that we apply g to x. So g must be a function. So we can see that g is a function. So let's do this. And we apply f to the result. So f must also be a function. So it's something like this. And now, okay, we have x is of type A, and we apply g to it. So g must be a function that has as the codomain the same type A. And let's call the domain B. And we see that f is applied to this result. So the codomain of f must be B. And then there is some result type C. And this is also the result type, the type of the right-hand side. So it's the overall result type of this function. So that's the signature. So it's called composition or function composition, because you have two functions f and g and you compose them. And there's also on the slide, so this is what we just did. This is the diagram. So you have a function g from A to B and the function f from B to C, and f dot g is the composition from A to C, which first applies g and then f. And it's sort of the wrong way around, but that's how mathematicians do it. So those of you who do math, we use this little circle symbol for composition, so the dot is supposed to symbolize that. I think there's also a version in the libraries where it goes the other way around. But this is like the mathematical composition. So you have the function you apply first in the second position. It's like from right to left and not from left to right. And this here could be, as we said yesterday and the day before, arrows are right associative. So this is equivalent to this. I could also write this, and this makes it maybe even clearer, that you have two functions as input and get a third function as output. And it's the composition. You have function from A to B and one from B to C, and you compose them to get A to C. Okay? And often we can build more complex functions just by composing simpler ones. So for example, if we want to compute the first 100 odd square numbers, before I get to that, in this example, we just need, just a second, computer must just wake up. Right. There's one function we haven't, I haven't shown you yet. That's called take, and that takes a given number of elements from a list. So if we ask for the type, it takes an int as first argument and then a list and returns a list of the same type. So what it does is it takes the first n elements of the list. So for example, if I have the list from A to Z, and I say take 5, then it would take the first 5 elements of that list. Right. So now to come back to this example. What was it? The first 100 odd square numbers. So what we can do is we I just want to see how it does it here. Okay. So we can start with the infinite list of all, or the almost infinite list of all ints. So now, and now I basically want to do this in one go. Right. The first thing we can do is, I mean, this is now the ints, let's square all of them. So we can do that with the map function. And what do we have to map? We have to map the function that squares. So we can compactly write that as lambda as this. So like this, it would be, I mean, just the infinite list or almost infinite list of all square numbers. Now we set only the odd ones. So I can use filter and, okay, filter odd. And now I can use this, and now I need parentheses or I need $. So this is now composition. So this means first I map, so I turn this list of ints into a list of square numbers. And then I filter, so I keep only the odd ones. And I wanted the first 100. So
why does the $sign solve the issue?
If it was like this, then it would expect a function on the right hand side of the dot, but it would then be bracketed like this, and then it's not a function. I mean, in the slides it's with parentheses, like so, which is the same thing. I can also do this. Okay, so in order to take the first 100, I need another composition. Let me just this. So it's a composition of 3 functions now with dot. So I start with a list of all ints, square them, filter the odd ones, and take the first 100 of that result. So we can try. Not very illuminating. Okay. Right. No idea whether that's right, but it looks right. I mean, it should be roughly to 200 because we only keep the odd ones. And 200 squared is 40,000, so 39,601 looks decent. It looks reasonable. Right. And in the beginning, we see it's like 1 squared, 3 squared, 5 squared, and so on. I mean, in this example, I could also have started with just a list from 1 to 1. No, that would have been wrong. So I mean, it's good. Yeah. Okay, so this is an example of composition. And so this is, I mean, very simple, of course, but often, I mean, extremely useful. And it's basically an incarnation of the divide and conquer principle. So you have a complex problem and you can just split it into simpler problems. So you solve a problem by splitting into steps and then do one step at a time. And you can, I mean, one way to express this is with function composition. And right, somewhere there was this, anyway. Right. So this is composition. Then general higher order functions are part of your toolbox for tackling programming problems. Recognizing something as map or filter is useful. And of course, you should never forget the standard design patterns that we went through. Was it day before yesterday? Yeah. But I mean, this is basically the most basic thing. The standard design pattern is like assembly in Haskell, sort of. So if there's nothing from libraries or no higher order function that can help you, then, I mean, if you really have to work and implement it, then you can do that. But very often you don't need to do any work because there's some higher order function or other library function that you can use. And composition, and I mean, Haskell is very good in like assembling pieces, and like the dot operator is one like fundamental way to compose things. And okay, function composition is a bit like a semicolon in the sense that, I mean, in imperative languages, the semicolon like joins statements together. So first do this, then do that. And as we saw, dot is very similar except for functions. So first apply this function, then apply that function. So in that sense, dot is like semicolon. But I mean, we just defined it, so it's not a syntactic part of the language. And there's also, later in a later lecture, we'll see another thing that's like a programmable semicolon somehow. So there are many programmable semicolons in Haskell. And this is, I mean, of course you can do something similar in every language, basically. But it's particularly powerful in Haskell because of the laziness. If you just look back at the example, I mean, I could just, if you just look back at the example, I could just start with the infinite or potentially infinite. I mean, if I change this here to integer, it would really be infinite. Maybe I should. I mean, the result will look the same. Stupid. So I could just as well change that to integer. The code stays the same. But now it's really an infinite list because integer is no largest integer. So it's, I mean, if you wanted to do this in imperative language, you somehow would have, I mean, here you can generate and filter or generate and check separately. So first of all, I mean, I don't care how, I mean, I just start with all possible integers because I don't know yet how, I mean, here we saw it was 39,000 something. So it's probably 199 squared, the last one. But I didn't have to waste brain capacity on figuring that out. I mean, I could just start with all of them. And then I do my processing, and in the end, I keep the first 100. And so I don't have to think about this. And in a strict language, you of course can't do this because then it would loop immediately because you can't ever evaluate this infinite list. So in a strict language, you would have to mix the generation part and this part. So typically in, I don't know, in JavaScript or whatever, I mean, you would probably keep a list of results or something and then keep count how many you already have. And then if you have less than 100, you would somehow look at the next integer and then do this thing. And so you would mix the generation and the how many you want. So, but here it's cleanly separated into these easy steps. Start with an infinite list, you do the squares, you filter what you are interested in, and then you take as many as you want. So yeah, in Haskell it's much more, I mean, more often useful to use this function composition, even though of course you can do that in other languages as well. Right. And partial application and anonymous functions help to keep such composition chains concise. I mean, this we also see. If you recall, map takes two arguments. It takes the function we want to map and the list. Filter takes, filter takes two arguments. It takes a predicate and a list. So these are again two nice examples of currying. So map has two arguments, but we only apply one, and what we are left with is a function from list to list. Same with filter. Filter has two arguments, we apply the predicate, and we are left with a function from list to list. And take also takes two arguments, we apply one and left from a function list to list. So we have three functions from list of ints to list of ints, so we can compose them. The types match up. So that shows it's very concise how you can write these things. And often, I mean, sometimes, I mean, this is lucky because for take, filter, and map, the list argument was always the second argument, not the first. If it had been the first, if they had been swapped, then I couldn't have done it like this, not so easily. No. But this is also like something that comes with experience. So often you have to pick wisely in which order you use your arguments, because often one way is much more useful than the other. But I mean, if it happens to be wrong, then there's also a way to fix that. Then it's just not as nice. Okay. This is the way to fix this. So there is a function flip that takes a function with two arguments and returns another function with two arguments, where the first two arguments are just flipped. So we have flip xy is just defined, flip fxy is just defined as fyx. Right. And that, yeah. So sometimes you are in a situation where you want to curry, but then it's the wrong argument, the second, but you need the first, and then if you use flip, you still can. And there's an example here on the slides. We have this for each function. I don't know, I've never used that, but whatever. So it's basically the map function, but with the arguments flipped. So the definition is just flip map. And then we can do stuff like example 2. Or let me call this one example 1. So I could now say for each and to 10 x to, I don't know, 2 times x. I mean, it's just map with the arguments flipped. Right. So maybe for some people this may feel more natural, and it's also, I mean, I don't know. I've never seen that, but something like an equivalent to that, like monadic form, is very useful. So I mean, as I said yesterday, Haskellers hate parentheses. In this case, the function I'm using there is very. If you use map, you would need parentheses, right? I mean, the map version would be. So this would be, I mean, by definition of for each, that would be the map version, and then we would need to put our function in parentheses, which in this case is fine, and actually in this case I can also use, I mean, in this case I could just do this. We talked about operator sections also in the first lecture. So then of course it's really doesn't matter anymore. So in this case, I mean, they are both equally simple. But you can imagine if you have a more complicated function that maybe spans over several lines, it would somehow be not clear to read if this complicated function is in the middle, maybe several lines, and then at the end there's this short dangling list. So in cases like that, often in Haskell we prefer if the long thing is the last argument, because then you can use the dollar, and then it's much cleaner, it looks much cleaner. So sometimes this would make sense to have a function like that. Right. Flip for each. Okay, query and unquery we already saw twice or at least once. So don't have to talk about that. So now to something new. Let's revisit the standard design pattern on lists. I'm wondering whether I should. Okay. So we have seen many examples of that. We defined a function fun on list of some type and got some result. And we try to internalize the standard design pattern on lists, which is to first, list has two constructors, non-recursive one and recursive one, so we get two equations, and the second equation can recursively call the function we are defining on the tail of the list. So this is basically this is not valid Haskell, of course, but this is the standard design pattern on lists. So we say what it does for the empty list, and if it's a non-empty list, we say what it does then. And in the definition here, we can use the head of the list, and we can use the recursive result of applying the function we are defining to the tail of the list. Okay, and we have seen many examples of that. And Haskellers hate repetition and boilerplate. So there's some boilerplate here, because it's always the same thing, and then one naturally tries to abstract that away and make it shorter and make this pattern clearer and more explicit. So, and there are two interesting things here. So we have to say what happens in the empty list case and in the cons case. And let's just give names to those things. So in the empty list case, we must write something. Let's call it nil. Nil and cons comes from, that's Lisp. So in Lisp, which is one of the oldest higher programming languages from the 1950s, Lisp is short for list processing. So lists are everywhere. Basically everything is a list in Lisp. Even Lisp programs are lists. And there they call the empty list nil, and where we have the colon, they call cons. So you cons a head to a tail. So that's where this terminology comes from. And right, so let's call the result of the function we are defining, applying it to the empty list nil. And then in the recursive case, we said it's some function cons that gets as input the head of the list now, and the result of recursively calling the tail. And of course, at the moment, this wouldn't compile because nil and cons are not defined anywhere. But we can fix that by adding them as parameters to our function fun. So we have two more parameters, cons and nil. And then in the empty list case, the result is nil. And in the non-empty list case, we take this cons parameter and apply it to the head and the recursively applying fun cons nil to the tail. And now all that's remaining is to figure out the types of cons and nil. And that's, again, exercise. You could, of course, just write this and then the compiler would tell you, or the editor. But if you want to do it by hand, we see here from the first equation that we use nil here as the end result. So the type of nil must be some result. And then we see that, x is the type of, is a list element. So x must be of type some type. And fun, cons, and right. And here we recursively call our function. So the type of this parenthesis is some result. So cons takes some type and some result and produces some result. So we can figure that out as well. So this would be that. And now, of course, normally we don't use such long names for type variables, so we can make that shorter. Like this. Right. What's the difference here? Right. And then it's not called fun, it's called fold R. right fold, I mean that's for right folding. So we call it fold R. So the only difference between these two slides is that the fun is now named fold R. And finally there is something that we haven't seen yet. So we talked about local declarations and I introduced you to let-in, the let-in construct. And there's a second one in Haskell that's the so-called where clause. And that looks like this. So I mean the point is that this const nil, we are always carrying that around. So here in the recursive call we drag that with, but we don't do anything with it. We just always pass it through. So it's a bit shorter and cleaner to implement a helper function, go, which has this const and nil in context. So that would look like this. So where clause comes like afterwards, and it's indented, and then you can do like local definitions here. Can be anything, I mean can be functions, can be constants, or whatever. And it can use everything that's in context. So in this case, these arguments here, const and nil, are in context for the where clause. And then you can use whatever you define here in your equation. So, and that's sort of, I mean, there are some differences between let and int about scoping and so on, but it's also mostly a matter of taste, whether you prefer let or where. I personally much prefer where. Right, and here's another thing that maybe makes you wonder, because if we go back here, we had 3 arguments to our fold right, and now suddenly we only have 2. And this is something called eta reduction. So we have, I mean, if you have, let's say we have a function x from a to b, then I could define a new function with lambda that sends an a to f applied to a. So I have a function f, and now I define a new function using lambda expression that takes an a and maps it to fa. And those two are the same. I mean, syntactically they are different, but they are the same. So if I have a function, then I get the same function if I look at taking the function that maps an element to the result of that function. And this has the fancy name. Those are the same, and there it's called eta reduction. And there's also alpha and beta reduction, or at least beta reduction. Right, and this means that if I have in Haskell, if I have something like this now, this fold R, what was it? So let me just not make a mistake. A to R, and an R, and a list of A's, and returns an R. So normally I would write fold R cons nil x's equals go x's, and where go nil and go cons y go y's. Right. And now you already see here this, that says eta reduce. Found this, why not that? So if you have something like this, where you have an argument that's just repeated at the end again, then you can just remove that. And that's called eta reduction. And I mean, for beginners, I suppose the other one would be clearer, but the more experience you get, the more you will appreciate this. And one other thing, I personally, I mean, but I'm a bit pedantic in that regard, I would put this type signature here as well. I would say it's from, which would probably in this case not work. Yeah, so in this case you can't with scope type variables, but I don't want to go there now. I mean, in this case, I can't. Let's worry about why not later. But you are allowed to put type signatures there. In this case, it's because it's polymorphic. It's a bit tricky. But if it was just ins or whatever, so I normally put type signatures everywhere. I mean, in my where clauses as well. But that's also a matter of taste and experience. Sometimes it's so obvious what the type is that you don't need it. But I always find it helpful, personally. So I would rather, like, also, I mean, the rule of thumb is only top level signatures are needed, but I normally personally also put signatures in where clauses to make it clearer. Right, so that.
So also sometimes when you have a cryptic error message that you don't fully understand, put in a bunch of the signatures, make it like easy for the compiler to return with the name that you are actually using.
Mm-hmm.
We will make it for a clearer error.
So, and basically now everything that we did yesterday, no, day before yesterday, as examples for functions defined on list, we could now rewrite in terms of fold right. Let's just do 2 examples. We had length. Let me just hide length again and filter. So length takes the list of arbitrary type and returns an int. And we implemented that using the standard list pattern. And now we can use fold right. So we must say what is the length of the empty list, that's 0. And we must say given a head and a tail and the length of the tail, what's the length of the list. So, and that's just one longer than the tail.
Yeah, you have to hide for.
Oh yeah, right, of course. Did I do something wrong there? Obviously I did.
It is autocorrected to filter.
I'm sorry?
You are trying to hide fold R, then it's changed to filter while you are typing.
Oh. No, I think that was okay. This is just my, each time I save, my formatter sorts the things in the imports alphabetically. Must be some stupid mistake, just a second. I mean, this is because I now hide filter, but I will re-implement this. Probably the order wrong. A to R to R. A L to. Oh, sorry. For whatever reason, with fold the cons comes first. So I did the 0 first, but if you look here, I mean, first we have the recursive case, and then we have the. I can never remember that either, but anyway. But it does make sense. We will see later why it's like this and not the other way around. Okay, and now of course we could make this here much simpler, like so, using operators section. Why is this now complaining? Ah, sorry. No, we can't. Just a second. Right. So now it's correct again, but I'm not using the A. So I mean, one way to fix this would be to use an underscore. I mean, that we have always done. Another way is right in the beginning, as an example of functions, I gave you this const function and said that looks stupid, but sometimes useful. So this would be an example where it's useful. So instead of writing it like this, I could also say const L goes to L plus 1. And now I can actually do what I wanted to do in the beginning. So now it's very nice and compact, and that's length. Okay, and filter. So we have a predicate and our list, and return another list. Predicate P. So that's fold right. So now here is the recursive case, but first the simple case. Empty list filtered is again the empty list. So now let's worry about that. So we have, let me just see how it's done here. Okay, inline. Right. But maybe it's a longer line. Okay, so we have the result, and we have the new head, let's call it X, and we have the filtered list, I mean the recursively filtering the tail, and now we must say what the end result is. So that depends on whether the head satisfies the predicate or not. So I can say if Px, then I keep the head, and otherwise I don't. So that would be filter. And we can also do concat. I think that's another example in the slides. So this plus plus. So if I have two lists of the same element type, I can concatenate them. Sorry, must peek. Oh, there's these examples. Ah, yeah, there's plus plus. Right, yeah, this is super cool. So XS, YS. So this can be written very compactly like so. Let me just write it first, then. Oh, other way around. Sorry. No, like this. Okay. Right, this is, I mean, this is almost magic, right? So let's see. So I want to concatenate X's and Y's. So the first, in the case that X's is the empty list, the concatenating the empty list with Y's is just Y's. So that's this Y's here. So fold right, so this is the nil case. So if X's is empty, then the result of concatenating is just Ys. Okay, now I must say if XS is not empty, if I have a head X, and if the tail of X concatenated with Ys, I already recursively know. How do I use this intermediate result given my new head to get the overall result? And that's just consing. So I must take my head and cons it to the result of concatenating the tail with Ys. So this is very cool and short. There is, I think in the slides are two more examples, two functions we haven't seen yet, all and any. Both take a predicate, no they don't, sorry. No, they just take a list of bool. There's other versions with, anyway. So I have a list of booleans.
Something happened, Lars, and everything got deleted.
Really? Oh, yes. Okay, all and any. Takes a list of booleans and returns a bool with the hopefully obvious meaning. So all checks whether all elements in the list are true, and any checks whether any element in the list is true. And those are both super simple one-liners now. So all is fold right and true, and any is fold right or false. And why does it complain? Oh yeah, because I didn't hide it. And now it's still complaining.
Yeah, because hard-coded.
Oh yeah, because the linter has that hard-coded. So yes, but right. So how can we understand that? So this says if it's the empty list, it's true that all elements are true. So that's, I mean, this is, some people struggle with this concept, but I mean, if I say for all elements in the list, I mean, there are certain, I have a list of conditions, they must all be true, then this is the case if there's no condition. Because then I don't have, I mean, I have to check for every single thing that it's true. If there is no such single thing, then it's automatically true. So this is the base case, true. And then if I have now a longer list and recursively I already know everything in the tail, whether it's true, then to decide whether it's also for the longer list, for the cons list it's true, everything is true, I must just end the head with recursively ending the tail. And here it's like the dual case. So the empty list, there is of course no true in the empty list because there's nothing in the empty list, so it's false. But and then it's all odd together. And so we could check. I mean, we can try this. We can't.
Because you changed the definition of the concatenation.
No, it's something else.
Yes.
Oh, here, yeah. Oh, sorry. Oh, yes. Oh no. Fold right colon y. Okay. Okay, now it compiles. So all true, true, true. I thought I hit it. Oh, and sorry. Right. And if I make one of those false, then it's false. And any right. And there's a, let me just, this is much later, but let me just, I think that's helpful anyway. So we will come to fold L, I mean I skipped it, I will go back of course. But I think this is maybe also helpful. So fold right takes this function, and it's here, it's, I mean, this is of course a Unicode character, but this is just now symbolic, this slide, I mean, it's not valid Haskell. But this is one way how you can think about it. I mean, if you figure out what, I mean, if you go through the definition of fold R, so you have fold R with this reduction function and the base case applied to a list, then if you do this by hand, the evaluation, then you will get this. So it starts with an E and then basically applies this operator here for each element starting at the right and bracketed like this. Now we will also, I mean, you can ignore this now, but this will be the next topic. There's also a version from the left. But this is also why it's called fold right, why it starts basically folding the list into a value starting at the right. So it starts with E at the right, and then it maps using this first argument of fold right the elements to it. So I mean, for example, in this all now, I mean the E was true and the plus thing was logical AND. So then that would be true and Z and Y and X, which, and in the any case it was false and or, so it would be false or Z or Y or X. So well, we didn't have sum yet.
We saw it yesterday.
Right. Right. So if for example this was plus, like a arithmetic plus, and E was 0, then it would be 0 plus Z plus Y plus X, so it would compute the sum of a list. Although that would be inefficient, we would use fold L for that, but we do that later. This is maybe a good way to memorize it. And there's also something cool, the identity on lists. I think that's not in the slides, but I think it's cool anyway. If you have, like, let's call it it list. If you use this, then it's the identity on lists. So if we go back to these slides, so the E is now the empty list and the plus is the colon operator. So, I have the empty list colon z colon y colon x, which is exactly the definition of the list x, y, z. So one way to think of fold right is that it replaces the empty list with this e and the colon with this e operator. So I mean, you have a list x. I mean, this is just syntactic sugar. We learned in the first lecture or so that actually a list. I mean, this list is just syntactic sugar for x colon y colon z colon empty list. And what fold right does, it replaces the empty list with e and all the colons with this operator you give here. So that's one way to look at it. And therefore, if you use colon and empty list for the two arguments, then the replacement doesn't do anything. So you end up with the original list. So that's maybe also a way to understand it. And that also helps understand why the parameters are in this order and with this signature, so that Cons and Neil fit there, or at least in this signature. Yeah. Right, so maybe we should have a short break and then do fold left afterwards, except if there are questions to fold right. Yes? Recursively do this. So I have to keep the 1 in memory and then recursively compute the sum of the rest. Then I have to do that. I have then to keep the 2 in memory and then recursively do the rest. So I have to keep the whole list in memory, basically, to compute the sum. Whereas in every reasonable programming language, that should be O of 1. I mean, it should be constant space, because you can forget the elements. And with fold L, or a variant of fold L that we will see after the break, you can have it in O of 1. Right. So other questions? Yes? I'm sorry? I always push that. You mean now, or?
Yeah, you push it now.
I can push it now, yeah?
Yeah.
Sure.
Any other questions before the break? So like you can push it while everybody is resting.
Okay, then I push it.
Yeah.
Oh.
It's a simple question. When we fold right and when we fold left, we only write the E character once. Is it for redundancy purposes, or why exactly is E appearing only once in the equation, whereas it could have appeared every single time?
Well, E is only for this empty list case. So that only, I mean, that's only one case. And I mean, a list, there's only one empty list, but then, there's only one base case. But then, any non-trivial list is comes from this base case and then by successive application of cons. So you need for each extra element in the list, you need this cons step, but you only, only at the very bottom at the base case do you have one E one. Okay. Okay, let me push this. Okay, should be pushed now. Does it work?
Sure.
Okay.
It's running. Try to start
Okay, now I pushed it. Okay, let's continue. Just some rules whether you should actually use fold R or just use the standard design pattern. And the advice given here is that you should, because it makes it clear for the reader that you are using the standard design pattern. So fold R basically signals
arbitrarily
directly that this is the standard design
zero, I
pattern
think, with
on
some
lists.
extension, but at least one.
But there
I
are
mean,
also
one to
cases,
many.
some of them are in the exercises,
And they can
where you
have like
can
arbitrary
implement a
signatures.
function
I think they should
with
mention
fold
the
R,
A
but
somewhere,
that is
but
like overly
can
complicated.
be anywhere.
I think
Or
take
left hand side,
is an
right hand side.
example.
So we will see examples.
There's an exercise where you can implement
More
take
examples.
using
So
fold
this is
R,
just this equal,
but
and
that's actually quite tricky to do that and
this
not
default
very
stuff at the
enlightening.
minimal.
So in cases like that, it's easier to just write it directly, the code. But in cases that, yes? Yes, now I did. Earlier I pushed. I'm sorry, you're struggling what?
No, it's not yet uploaded.
The code, I pushed the code.
Yeah, but
arbitrarily many.
Did you ask for
Can
the
even be
slides?
zero,
or-
I think, with some extension.
No,
but
I
at
didn't
least
push the
one,
slides.
I mean,
I
one
can.
to many.
in the file.
And they can have
you
like
can, I
arbitrary
suppose.
signatures. I think they should
Okay, we
mention
push
the
the
A
slides as well
somewhere,
then.
but it can be anywhere. With left hand side, right hand side. So you,
Right. So you should, I mean, in easy cases like for concat, for example, or filter, it would make sense maybe to
arbitrarily
use
many.
fold R.
It can even be zero, I
Right
think,
now,
with some
to
extension,
motivate
but at
fold
least one.
L,
I mean, one to
Let's
many.
revisit reverse,
And they can have like arbitrary.
which was, I mean, we had implemented a version of reverse, and there's also something in the exercises, but seeing as not all of you have done that, let's maybe do this. Let me ask first height reverse. Let me call it prime now, the version we had. And I mean, we can now do that with fold R, let's say. So reverse is a list. So So the empty list reversed is just the empty list. And if I have a non-empty list with X as a head and X as and a tail, and the reversal of the tail is Y's, then what we did is we took the reverse tail and concatenated the X at the end. And the prime, of course, is wrong, sorry. Right. And we can try that this works. Sorry. Okay, that seems to work. Let me just try something. What was it? Set plus M?
Plus S.
Plus S, yeah. Let me just do something like length of reverse. Sorry. Right. But length, unfortunately, this is now a bit unfortunate. Can I do prelude length? No, I can't. Let me call this length here length prime that I defined here as an example. And not height length. Okay. And now if I do, I don't know, 100, it's still fast. Do 1,000. It's 0.17 seconds, and if I do 10,000, it's not just 10 times slower, it's like a lot slower. And intuitively one should, right, so you see it's like almost like 100 times slower for a 10 times longer list. And that, I mean, intuitively one should be able to reverse a list in like linear time, but this, I mean, this is no proof, of course, but it hints that it's quadratic. And so, I mean, even though it's correct, our implementation, it's inefficient. And maybe I should like evaluate again. I did that before, but now do it properly with list 1, 2, 3 to reverse it, to see why what the problem is. Let's try this. I mean, I've done that before, but then I stopped and said that's an exercise for the reader. So maybe, so 1, 2, 3. And let's write this now like properly without the syntactic sugar. Like this, okay. And I mean, the first steps are easy. So, I mean, this is now the cons case. So this is reverse of the tail plus the head as a singleton. Okay, let's write. Not sure that's necessary, but okay. And if I now want to reduce that, I mean the plus, I'm not sure, I mean, right, if Haskell wants to reduce this, I mean, this is a list, and I want to know it's the empty list or not, and so I want to, we always go from the out, so I would like to reduce this plus, but the plus, if you recall, it recurses on the first element and checks whether the first element is empty element or not, and if not, I need the head and the tail. So in order to do this here, I must evaluate this first part further. So this is again non-empty list, so it's again this. So I must recursively reverse the tail and append the head. Right, and now again, this first one again is a non-empty list, so I must recursively reverse the tail, append the head. Now, do I have enough brackets? Yeah. Okay. And now, what next? So now I can do the reverse of the empty list is now a base case, so that's the empty list. Okay, now what can I do? This plus, if the first element of two lists I want to concatenate, if the first is empty, it's just the second. So I can reduce this to just the second. Now I have this case here, so concatenate, and concatenating a non-empty list was I recursively concatenate the tail and then append the head, so it's So this bracket here now, it's 3, and then recursively plus. I hope that's right. Okay, so now here I'm concatenating an empty list, so that's again easy. Right, now this plus here, it's so this is a non-empty list, so I must recursively, I keep the 3 and then must do the rest. I think. Okay, now looking at here, I keep the 2 and must do the rest. This is the base case. And now I'm done. So now I have 3, 2, 1. I'm not sure whether this is already visible, but I mean, it's a lot of steps for a list of 3 elements. And I claim if I now did the same calculation for 4, it wouldn't just be like a little bit more steps, it would be like a lot more steps. And the problem is somehow this, that the parentheses are on the wrong side. And I have to basically shift them all to the right side. And I mean, they are it's exactly the wrong way around in order to apply the recursive base, I mean, to figure out the head. Yeah, so this is, I mean, one can prove or one can convince oneself that this is a quadratic algorithm and not linear. And there is, I mean, the proper way, I think that's an exercise, but we can do this now. The proper way is to, I mean, here we did, I mean, we recursively reverse the tail, and then at the end we put the head in as a singleton list. And the better way is to use an accumulator. So let me maybe just write it. So it's the same signature. So the idea is this first element now is an accumulator of all the elements I've seen already. I show how it works at an example of 1, 2, 3 in a second. So let me just write it. So if I have my accumulator and the empty list, I return the accumulator. And if I have my accumulator and the non-empty list, then I just put the X on top of my accumulator and recurse. And I claim that that is much faster. Let's see if we do this thing here with the, I hope this works without full, let's see. Yes, so now I can do the same what took me 13 seconds earlier in 0.02 seconds. And let's see whether it's also correct. I mean, let's remove this length thing. Well, yes, so I mean, it's correct and it's much, much faster. And maybe just to understand how this works, let me do the 1, 2, 3 again. So reverse 1, 2, 3. So it's go. In the beginning, the accumulator is empty. 1, 2, 3. So we are in the second equation. So we have our accumulator. So it's go. Sorry. So now I have to put the head of the list in front of the accumulator. So it's go 1 and the tail of the list. So now I again put the head of the list in front of the accumulator. the tail of the list again. And now I'm in the base case, and I just return the accumulator, which is, of course, what we wanted. So maybe from this one can already see that it's much faster than this thing. Okay, and this is also a common pattern on lists. Maybe a second example, like sum, even though this, I mean, that will still have problems. I said earlier why sum is maybe a bad idea to use fold right, because we have to remember all the elements of the list in order to make progress. So it will, in memory, it will consume the basically O of n of memory, whereas it should be in constant memory. So let's do this. Let's also call it sum prime though. So if we have num, so some things we can add. So we can use the same idea with this accumulator in principle. Sum is go 0 in this case. And go, so the accumulator is of type A. So go accumulator of the empty list is just the accumulator, and go accumulator of a non-empty list, I just add x to the accumulator and do this. Right, I mean, we can try this out. So sum prime of 1 to 100 int, so it at least works. Okay, and so this is also like a common pattern. So if you look at my implementation of reverse and of sum prime, they are similar. And this is again, and whenever we as Haskellers see something where we use the same pattern more than twice or maybe 3 times, then it screams for an abstraction. So same as we did for fold R. Let me go back to the slides. Okay, these are the examples, the same that I had. Reverse and sum. I hope it's done the same way. Yes, it is, I think. Okay. Right, and now the same that we did for the standard design pattern for lists. We try to basically see the common structure and abstract that away so that we have like something like fold R, but then using this accumulator pattern. So we see, I mean, that we have this helper function go, and we call it basically with the result for the empty list. So in the case of reverse, that was the empty list. In the case of summing, it was 0. And then we need this rule how in the cons case we update the accumulator for the recursive call. So in this case of reverse, our accumulator was acc and the head was x, and then the new accumulator was we cons x in front of the accumulator, and for sum we just add the head to the accumulator. So so this E is the case for the empty list, and then we have this op thing. So we do something in order to get the new value of the accumulator. We need some operation that gets the old value of the accumulator and the head of the list. And again, this wouldn't be well defined because the E and the op are not in scope. So again, as before, we add 2 new parameters, op and E. And then we figure out the types of op and E, or let the compiler do it. I mean, I can show you. Should I? Yeah, maybe. I mean, fold R I already have. Let's put fold L here as well. And this thing we will call fold L. So it takes an op and an e and a list. So it's go e and go acc empty list is the accumulator, and go acc xxs is go where we now update the accumulator, and just let me get it right. So acc x xs, right. And now the compiler tells us the type. And why is it complaining? Oh yeah. Right. So it's again eta reduction, so I can get rid of this e here. And of course the names are a bit silly. I mean, of course it's perfectly fine, but we normally use ABC or something. So let me, I don't know what's the choice in the slide. Okay, the list elements are A. So this T2 is A. And the result is R in the slides. So let me call T1R. So I mean, it's very similar to fold R somehow. It's only the R and the A are swapped around. But the operational, it behaves differently. As we saw, it uses this accumulator. And now we could write, for example, our sum prime, we could define instead as, oh no, something bad, yeah. So let's call it sum prime prime. We now could write as fold left plus 0. Yeah. And of course there is a built-in sum. And the reverse we could write as, let's call it reverse, I don't know, prime prime. Fold left. So what do I do? It takes first the accumulator and then the head, and it did this. So what does it complain here? Yeah. Okay, I thought so. It was just, so this would be another, I mean, it's almost cons, just with the arguments flipped. So I can alternatively here write flip cons. Right, let's just see whether this is still correct. Okay, it seems to be fine. Just check, so we get there as well. I think that's the same that I also wrote. So now we are the slide that I showed you earlier already. So it's very similar somehow, if you look at it like that. So the difference is that it now starts from the left. So the E is first, and then the things are one by one, starting from the left, accumulated in this result. Right, so this is the difference basically. I mean, the result is the same, of course, because addition is associative. Right. Right, and now if we now think we have our efficient summation, for example, let me see. So I have this sum plus, and let's try it out for what did I call it? Sum prime, sorry. No, double prime. Sum double prime, let's start small. Let's use integers for variety's sake. So that looks good. 100 looks good. Still not too bad. Sorry. Does it automatically optimize that maybe? Let's be a bit more ambitious. 10 million? Right. So first of all, it takes a while. 10 million shouldn't take that long. And secondly, it takes a lot of memory, like 2 gigabyte, 2.5 gigabyte or something. Yeah, which is crazy, right? To add up. Right, and so there's now another problem, and that is now the laziness. So, I mean, as we learned in day 1, Haskell is lazy and only does what it has to do. So it doesn't evaluate anything, it only evaluates if it has to. And if we look at this definition here, so in particular, it only evaluates the new value of the accumulator if it has to. And while the recursion is going, there's no need to. So what that means is, if we look back at the slide, here, for example, it won't evaluate this first part here until the very end. So, it has this whole expression in memory, and only then it's forced to evaluate it, because I wanted to print the result to the screen, and then it does that. So that means even though basically the whole list in principle is, it no longer needs to remember the list elements like for fold R, but somehow it still does, because they all reappear here in this accumulator, because it doesn't evaluate this. What we want is that basically it doesn't keep this around. It should, start with 0 and then just, immediately add 1 to it and compute that. And then the next have the accumulator value 1. And then add 2 and compute that. So use 3 and 6 and so on. But it doesn't do that. It keeps this, this unevaluated computation, that's a so-called thunk, in memory. And that gets bigger and bigger because the list is so long. And only when it's forced to produce a result does it actually evaluate that. And up till now, we haven't learned, there's no way for us to fix that. So because we can't force, we don't know, or you don't know, how to force Haskell to evaluate. And with what you know about Haskell right now, you can't. But there's a primitive in Haskell that allows you to evaluate, to force evaluation. And this is seek. So that's, if we ask for the type of it, SEQ, it looks very strange. It looks like the type of const. So it takes an A and a B and produces a B. And from the type you can already see it will just give the given B. So semantically it's the same as const. It ignores the A and returns the B. But it's special, it's built in, it's like magic. And what it does is, if you evaluate B, then, if you evaluate this seek thing, then it will first evaluate A and then return B. And so this is Haskell's primitive. There are like higher level things built on top of it to make it easier to work with it. But that's the primitive to allow us to force evaluation. So let's try to, and this is then called fold L prime. So let me just copy my fold L and let me hide fold L prime. Oh, no, I don't have to hide that, that's not in the prelude, which is weird. Anyway. Right. So let's just slightly rewrite this here. So let's make it a little bit more verbose. Let's give the new value of the accumulator a name and use this here. Now I didn't change anything. It's just longer. But so what we want, or what the problem is that this egg prime is not evaluated. So if the list becomes longer and longer, I mean, this computation gets longer and longer and it doesn't get evaluated. And using seek, we can now evaluate that. We can do, does he do it here? Sorry. Right. So now we can use the seek. So we can evaluate this. So we can do it like this. Or on the slides it's actually written inline. So seek for sequence, which means that basically it forces Haskell the runtime to evaluate this, the first thing before it goes on with the second thing. So semantically, as I said, because seek is like const, like if you just look at the values and ignore the efficiency and the runtime, then it's exactly the same as fold L. So the logic is exactly the same. But now it will immediately evaluate this egg prime. And now we hopefully see an effect if we use some, I don't know, I could use triple, but let's just call it turbo sum, which hopefully works now. Be embarrassing if not. Okay, let's just, so recall for some 1 to 10 million, it took more than 5 seconds and 2.5 gigabyte. And now hopefully we see an improvement. Not so really. No, that's it's even worse. So what did I do wrong?
No, it's better. It's 3.3 instead of 5.2.
Yeah, but the memory is still far too high.
Same.
So I did something wrong. I mean, okay, it's faster, fine, but the memory should not be that high. I mean, this is, the indentation is wrong, but that's not it. Maybe, no, that's not it, is it? I mean, I could inline that again, but I doubt it's that. I mean, I could write op arc. No, I can't. I mean, I can use the bank pattern thing.
Yeah, we have to introduce.
But
no, there's no need to introduce.
let me just try something quickly. I mean, this is anyway on the slides. Hang on. But this is a bit anticlimactic now. Let's see. Okay, it's a bit better, but I mean, it's still far too.
What is this? The slides the same?
I'm sorry?
The slides are the same?
Let's see.
Looks right.
Op E, go E, let's see. Well, I have the eta reduction, but that can't possibly be it.
There is an improvement, but still, like the memory should be almost nothing.
Yes. It's really.
Try with
I mean, maybe hang on. Probably this memory, that is like not the wrong. That's maybe not the right thing. But I mean, even so, it shouldn't allocate so much, right?
No, can you try with preludes for now?
Yes.
Right.
So let me now.
Double prime.
Yeah, let me call my version double prime. Should have tried that before. and now import. This is for some reason the fold R is not in the prelude, which is weird. That's in something called import data.list. I mean in list. So this is.
Still, the bytes are pretty high though. It's almost.
Yes. Okay, so this is some, I mean the official version.
Yeah, it's
And
highly optimized.
where it's highly optimized. But it's still a lot of, so maybe this memory consumption is somehow not misleading. I hope so.
I will check it out and go back. Yeah.
Yeah, so I come back to you about that.
Yeah.
But I mean, at least we did see some improvement from 5.3 seconds to 3 seconds. And the memory went down a little bit. But it should be, of course, all the way down. So I don't know why. But we'll investigate and let you know tomorrow. Anyway, and what I did here with this, let's go back to the slides, maybe they explain it better. So this is the version I had with the seek. And there is an extension that are now activated called bang patterns that makes that somehow nicer, so you don't have to explicitly write the seek. So this is an extension to the pattern syntax. So now you have this bang, this exclamation point. So you can put that in front of a pattern, and that then basically seeks it. So it means that this will be evaluated before it's used here. So it's the same as with the seek, but it reads a bit nicer. So this will first evaluate this before it goes on. But this is now exactly what I have, and I don't know why this is so bad. But yeah, anyway. But here it says somewhere that, I mean the second remark, that the official one is highly optimized. So there they have pulled all registers to make it as fast and efficient as possible. But in spirit it is like this. And the first remark is that this fold L, you should immediately forget again that it exists, because there is some, I was once interested whether there's ever a situation where fold L is better than fold L prime, and there is some obscure Reddit, subreddit, thread discussion where I think Duncan came up with a super complicated example where indeed it might be better to use fold L. But I mean, as a rule of, I've never in my life used fold L. So I think you can just forget that fold L exists. So if you have an accumulator, it almost always makes sense to immediately evaluate it. So this fold L, and therefore it is so strange that fold L prime is not in the prelude. It's a bit irritating because you use it all the time, and I also use it much more often than fold R. This is very common. Are there any questions at this point? Okay, so that's fold. Yeah, question?
You said the exclamation point is called a bang pattern,
Yes,
and it does the same work as seek.
yes.
So instead of writing seek, I can just put an exclamation mark and it will tell it execute this first,
Yes,
and then continue.
yes. So when you use this, the pattern, I mean, it's called, I mean, that's bang is another word for this exclamation point, right?
Yeah.
I mean, it's also she bang if you have like
A bash script.
a bash script.
Yeah.
And pattern, because it's a pattern. I mean, it's on the left-hand side of an equal sign. So you can decorate patterns with this exclamation point, with the bang. And then what it does, I think, is that it, I mean, where you use it here, it will seek, so it will seek the rest of the computation with this. So it will force that whenever you look at the rest of the computation, you first evaluate what the pattern matches against.
It's not necessarily better, because it's not
Right.
that it speeds up the computation. It evaluates, but there are lots of cases where it's wrong to evaluate it before it's needed.
Yes.
Because the compiler can, like, if it's lazy, the compiler can do all sorts of stuff to make sure that everything is super smooth. If you force it to evaluate it, there's a bunch of optimization that it cannot do. So you have to know when to use it.
Yes, that's also, I mean, I love Haskell. I think it's the best language ever, but it can be tricky with things like that. I think I've once listened to a talk at some Haskell conference where somebody used like AI, or at least like random. I mean, he had like some program, and then I think he tried like randomly putting bangs somewhere, and just seeing which version was the fastest. So it's very difficult somehow to get that right. So it's good to rely on library functions like fold L prime. I mean, they are tested, and I mean, they're used everywhere. So that in that case, it's certainly the right choice to put the bang there. But you can't think that putting bangs everywhere will make everything better.
You know, you have profilers also. You can profile your, like you see when the memory just grows like crazy, and say, okay, I need to evaluate this to know how to sort it. There's way to methodically go through it, but the default being lazy is great.
But for those of you who are mostly interested in Plutus, I mean, the good news there is that Plutus is not lazy.
No.
So this all doesn't matter for Plutus.
Computation beforehand.
Yes. So Plutus looks a lot like Haskell and uses the Haskell compiler, but it's different. It's strict. Right. Now what's next? Right. And some of the things we have seen, let me just see what they do. I mean, these things, I mean, we have seen them for lists, fold R, LM, filter, map, but they would also make sense sometimes for other data structures. I mean, for example,
Chain?
yeah, for example, the chain. I mean, fold R, one way to look at it that I told you was we replace each colon with this operation and the empty list with this E. And that would also make sense for other data types with other constructors, that you somehow have a tree or whatever, or chain, and replace every constructor with some function. And, or LM to check whether a given element is somewhere in the data structure. Or filter to, I mean, this is like more questionable whether it makes sense for things beyond lists, filter. But anyway, you can at least ask yourself. In map, we saw, for example, with tree map yesterday as an example, that you could have a function from A to B and then a tree of A's, and it basically replaces each leaf of type A by applying a function to it. So that would also make sense. And for some of these things, Haskell has type classes that are basically already predefined. One of them we have seen on the first day. Now we can look at it a bit more with more understanding. So one is class foldable T. So T is now not a simple type like int. I mean, T is something like list or maybe that takes a type argument. And that is one of the things that make the Haskell type system so super powerful, that it basically the type variables don't just refer to things like int or bool, but can also refer to things like list or maybe. So that makes it extremely powerful, the type system. So foldable T, so T you can think of as containers. And this looks like a lot, and there are even more. I mean, we can ask for information on foldable.
Should we talk about kinds now?
No, I think that comes later.
Okay.
Another lecture next week. So we see there's lots of stuff. But we also see that fold map we can also talk about later. But for example, it's enough to implement fold right. And fold right is, where is it? Here?
Maybe you can import data foldable to make
Yes, yes, yes. So now it looks a bit nicer. But still, oh yeah, because fold right is now double defined. Anyway. Right, so this is almost like our fold right, except of the list of A, we have TA now. So it's not just a list, it's an arbitrary foldable. And so the way to think of foldable is something that can be converted to a list, or that's the way I think of it. So, I mean, lists obviously are foldable because they already are lists, you don't have to convert them. But for example, we had our flatten function of the tree that took all leaves and flattened them into a list. So that hints at the fact that tree might also be foldable. And there are other examples, for example, maybe. So if we look at here at the instances, I mean, we see our lists. That's no surprise. I have no idea what solo is. Never used it in me life. Maybe. this is interesting. So how is a maybe a list? Well, I mean, a maybe, if it's a just, it's a list just containing this one element, and if it's nothing, it's 0. And we come to either and pairs in a second. That's a bit controversial. But the cool thing is, I mean, why do we want something like foldable? Well, it means that as soon as you have an instance, all these functions are available. So, for example, if we make our tree an instance of foldable, then we automatically have sum, which sums the leaf values in the tree, and we automatically have length, which counts all the leaves in the tree. We have null, which sees whether there is at least one leaf in the tree. We can convert it to a list, so we wouldn't need to write flatten anymore. The biggest leaf in the tree, the smallest leaf in the tree, product of all leaves in the tree. So all these things you automatically get for free once you have an instance of this class. Right, and we can, for example, try that out for maybe. So, for example, toList. Let's say toList, just x is, maybe I shouldn't use, I mean I can, but let's use booleans. So if it's a just, it gives you the singleton list with just that one, and if it's nothing, now I must help the compiler and tell it what I want, a list of booleans, and it gives me the empty list. So it's not very exciting, but I mean it works. And in particular, I could do something like sum just 42, and that's 42. And if I have sum nothing, then it's 0. I mean, which sort of makes sense. We will see more interesting. I mean, it's just, yeah. So maybe it's basically, it can be, you can think of a maybe value as a list with 0 or 1 elements. Now we saw here that pairs are also instance of foldable, and this is a bit weird. So pairs always have exactly one element, and it's the second one. So if I do toList of a pair of a boolean and, or let's say of a pair of a character and a boolean, it ignores the first element of the pair and it returns the singleton list containing the second one. So that is controversial. I mean, it's okay. I mean, like mathematically, it has all the properties it should have, but it's confusing some for people. So for example, if I ask for the length of this, because it's foldable, so I can ask for the length, it will say 1. Because length is basically the length of the list I get when I convert to a list. And I mean, I think intuitively one would expect that the pair has length 2. But it's basically, I mean, it ignores the first element and just looks at the second. And the same for either. So either only considers the first one. So if we have toList write true of type either character boolean, then we get the list containing this true value. But if we take a left one, left C, then it's the empty list. So for either it's like maybe a bit, but it only looks at the right value. So if it's a right, it returns the list with that element. If it's a left, it returns the empty list. So I mean, even though either and pair are instances of foldable, they are a bit strange, and I don't think that many people use them. But sometimes it can be useful. But much more useful for lists or for things like our trees. I mean, should I implement fold right for trees? I think that's an exercise, or
Yeah.
it's an exercise. Is there another type one could non-empty list use? I mean, that's
The non-empty list, but are we doing that in
with the packages and tools, or?
yeah.
Okay, I think that's an exercise for you to implement. Maybe for chains, I think that's not an exercise. I mean, we have these chains, our blockchains that are defined here, And I can, for example, make chain an instance of foldable. So instance chain, foldable chain, where, so why now, yeah, okay, I have to implement, for example, fold right. And now, for example, now I find it helpful that I have this instance sig that I told you right in the beginning of the lecture, that I can give the signature, because for complicated functions like that, I personally find it helpful if I know what I'm supposed to implement. So I have A to R to R to R to chain A to R, I think. So let's call it, I don't know, op and E, like in the slides. So if it's the Genesis block, then it's E. And if it's op E, let's see. It's a bit strange, right? So it's a block of another chain and the transaction, the A. So it will be op A sorry. Is it now fold R op EC? I think I can, because I have another fold R in scope, right? Can I write data foldable?
Maybe change the other folder.
Yeah. Sorry. Where did we have fold R? Here. So I rename that to prime. Oh, sorry. I haven't imported this here. Foldable. Probably from data foldable. Yeah. Oh no, I don't want to hide it anyway. But it's in data foldable, so I have to implicitly, it's not in the prelude. Now I have two errors, right? Yeah, because it seems there is a fold R prime. I must hide that from somewhere. Hang on. Problem is now there's a fold R prime in data foldable, whatever that does. It's a strict version of fold R probably. I can't really hide that, can I? No, I can import foldable and just fold R. Okay, now I still have another error somewhere. No, now it's fine. It's just a warning. Okay, just a warning that here I don't need this. Okay, seems to compile again. And not sure this does, I mean, it seems somehow wrong because it's the wrong way around, but whatever. Right, so now we could try that out if we have an example chain. So I don't know what example chains we had in the, let's say, chain int. And we had this operator, but I forgot what the precedence was. I just do it by hand. Block, 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 3, 4, 10. Okay. Right. And now, because I've made this an instance of foldable, I can, for example, use toList on it. And this is what, yeah, okay, it's fine, actually, I think. So, I mean, it's now the other way around and it appears there, but it makes sense. I mean, the chain grows from the genesis block and this grows from the empty list, so it's fine, sort of. So yeah, I mean, so now my chain type is of type foldable by writing this fold R implementation, and now automatically I have everything that's available for foldable. We saw this long list of things, and of course other functions that may use that is now automatically available. So for example, now I have sum available for my chain 1, which sums all the values if it's a numeric type. Or product. Or I can check whether it's null. So chain 1 will not be null, but genesis block is. So yeah, I mean this is, and I mean the intuition is it's a foldable T is a type where TA is a container of A's that are in some order. I mean that you can convert it to a list. But it does not have to be faithful. So a tree, for example, if you flatten a tree to a list, you lose information because you forget the shape of the tree and just remember the leaf values in order. There's another type class that we'll look at quite a bit later, traversable, that somehow remembers the shape as well. Right. Foldable, probably another break. Just wondering what's next. Okay, we talked about maybe. We talked about pairs. So it's especially confusing. I mean, in my example, I had different types for A and B in the pair. I had character and bool. Here in the slides, the same type is used, int. And this is really confusing. I mean, you have two lists of a pair containing 3 and 4, and the result is 4. So the 3 is dropped. As I said, the first component is ignored. So this is a weird instance, the foldable instance for pairs.
This is like an intuition. It's a tag value. The first one is the tag, and the second is the value. So when you fold the values, not the tags.
Yes, so it basically considers pairs as tag, where the first component is a tag, a name, a label for the second one. Either I also showed, so that we have done that. Okay, and now this is functors, but I think we should have another break probably.
And then I think that's it, functors.
Yeah, let's see. No, then there's this. So it's 2 topics left. Functor and katamorphism.
And then we have the tooling.
Yes, do it. And we can also do the tooling tomorrow if it's better.
Yeah.
Right, but I think we should have a break.
10 minutes?
10 minutes, yeah. continue. Let me just repeat once again this tree type. Oh yeah, no, sorry. Just want to see. Right. This tree type, so we had data tree, a tree with A's in the leaves. So it could be a leaf or it could be a node which has two children which are trees again. And I think I already had this example map tree, which given a function from A to B, and a tree of A's turns it into a tree of B's. So if we have a leaf with an A, then we turn that into a leaf with F applied to that A. And if we have a node with left and right child, then we return a node where we recursively map tree F over the left child and map tree F over the right child. And as an example, I don't know, character. It's still on the, oh yeah. Okay, let's do this again. What's on the whiteboard? So there was a 7 on the left. And on the right was a node with 4 and 9. Div. Okay. So if I have my tree and I can now, for example, map tree, whatever, function that squares. And now I get a tree of the same shape, but the leaves, to the leaves it has applied the square function. So instead of 7, 4, and 9, I now have 49, 16, and 81. And then we had maybe, and I think we had map. Okay, that's not in scope, good. So we also had something similar for maybe. Let me put this, I don't know, somewhere here. So map maybe, given a function from A to B, and a maybe A, turn a maybe B. So if it's nothing, I have no choice but to return nothing. But if it's a just A, I can return a just F applied to A. Right. And so these are these. And remember, we also had map for lists that takes a function from A to B and turns a list of A's into a list of B's. So we now have 3 examples that are very similar again. So we have some sort of container or thing that takes, I mean, a constructor that, a type constructor that takes a type variable, lists, trees, maybe, and then we have functions that given a function from A to B contain a thing of A's into a thing of B's. So list of A's into a list of B's, tree of A's into a tree of B's, maybe A into maybe B. And somehow it's always similar. I mean, it keeps the shape, whatever that means. I mean, in the case of lists, it keeps the length of the list, and it replaces each element by applying the function. For tree, it keeps the shape of the tree, but gets a new tree by applying the given function to each leaf in the tree. By maybe, I mean, also it's nothing but just, and it keeps the same shape, nothing or just, and applies the function to the value if it's there. So this is something that appears all over the place. And Haskell also has a type class for that to abstract that away. So, and that is called functor. functor f. And that only has one method called fmap. And there we see this generalization. So you have this f of a, and you can turn it into an f of b if you have a function from a to b. And we could now make our, I mean, for example, tree, I could using this map tree, I could make tree an instance of functor by using map tree as definition for fmap. I could do the same for lists by using map, and for maybes by using map maybe, but that's already in the prelude, so that's already defined. So if we reload and ask for information on functor, then we get all sorts of things, and in particular we get lists and maybes. So that's already predefined. So I wouldn't need to define this map maybe function. I could just use fmap and write. And there's also an right. So here one could define it like that, but the instance for list and the instance for maybe, as I said, is already in the prelude. And there's also another name for fmap, and this operator that I briefly showed once, one of the previous days, with this angular brackets and the dollar sign. So that's basically on purpose that it should remind one of the dollar operator, which is function application. So in a sense that it's also a sort of function application, it's just, I mean, different, because in the functorial sense. And often that's nicer to write that. So I mean, now because I made my tree an instance of functor, for example, I could do something like +1 tree, and I would add, so I would fmap the +1 function over my tree, and fmap is just the map tree I defined earlier. So this is a very common and very important class in Haskell, and we will see many examples of things that are functor. So the intuition is somehow you have some sort of container where you think it's not always true that it's like a container-like, but often, and you fmap by applying the given function to all the a's in the container, and then you get a container of b's. Right. So we now have seen two important more type classes, functor and foldable. Oh yeah, but before we go into that, this is now a new concept. Sometimes type classes come with so-called laws, and that's something that should hold for your instances, but the compiler can't check that it's true. So you have to convince yourself or prove it by hand, basically. I mean, nobody does that, I think. No, I mean, normally, but at least if you get more experience, you will get a feeling for it, whether it is like obeying the laws or not. So in the case of fmap, it should have two things. So if you fmap the identity, you should get the identity. So that means in our tree case, I mean, we have our original tree. And if I now fmap the identity function over it, we should get the same tree again, which in this case is true. And the second law is, if you have two functions, f and g, and you fmap the composition of the two functions, then that should be the same as if you first fmap the g and then fmap the f. So we could, for example, add 1 and multiply by 2. We get this, and that should be the same as if we first add 1 and then multiply by 2, and yeah, this in this case seems also to be true. And incidentally, it's not mentioned on the slide, but I think it's enough to check the second property, then the first one follows automatically for some like quite deep reasons rooted in the Haskell type system. Right, and as I said, the compiler can't check that. So you can write instances that don't obey the laws, but that's normally a bad idea because people using these type classes will expect that they do follow the law. And if they don't, then you get surprising results. I mean, people will expect that fmap identity, for example, doesn't do anything. And if it suddenly does, then that would be like lead to confusion. Right, and here's just graphically. So if you have this diagram we had for composition, so 3 types A, B, C, and function G and F and the composition, then there are 2 ways to go from FA to FC. You can, I mean, you have fmap G to go here and fmap F to go there, so you can compose the 2. But otherwise, you could also compose F and G and then fmap that. And the law is that those 2 things are the same.
Usually the laws are pretty straightforward and like intuitive. It's something that you will expect that 3 plus 4 should be the same as 4 plus 3. But the implementer of the function could like not follow that thing that you assume is right? So in this case, it's more like it's a statement instead of like leaving that unsaid. Like these laws should be followed for the user to have an intuitive use of your functions, right?
And not sure. Right. So there's also, I mean, there's something I haven't tried before. So in the REPL, you can also do :doc, and if you are lucky, you get documentation. It depends whether it's compiled with documentation or not. And in this case, you do, and you would get the same if you go on Hackage. So, for example, as for Google, let's say functor Hackage. I make it bigger just now. Just bear with me. So if we look in the documentation for functor, then it also states these 2 laws here. So normally, if there are laws, then you can also look them up in the documentation. So it's like a help for people using instances because they can should be able to rely on the fact that these laws hold, but it's like an obligation on people implementing instances because they should make sure that these laws hold. Right, and the good news is that even though that's not Haskell standard, GHC can automatically derive functor and foldable, and I mean also foldable. So we could have just not done that by hand. So I could have just left this. And just derive functor and foldable. For trees, we haven't done the foldable yet, by the way. And now I get errors because it says it can't. But for that, there are pragmas. So one is called imaginatively derived functor, and one is called derived foldable. So now I should still get the same, even though now I commented out this map tree doesn't exist anymore, but fmap now from the functor class gives the same result. And I can now also do toList on this tree because I also have a foldable instance. And that is our flatten. So we wouldn't have needed to implement flatten by hand, that's just toList from the foldable instance. And I'm not completely sure whether, I mean, I could do the same for chain.
Yeah, it should work.
Just not sure whether it's the right way around. Let's see. So here I explicitly gave a foldable instance for chain. I can instead, where was that? Ah yeah, you're right, very beginning. So I could do deriving show eq functor foldable. Let's see. Chain, was it chain 1? I thought I had next. Oh. Oh, because I did that by hand this morning, this afternoon. So I would have to comment this out as well, where I did that, to show you this instance thing. Okay, now it compiles. It was called chain 1. And now let's see what toList does. I think it's the other way around. In my implementation, it was 10.4.3. I mean, it makes more sense like this anyway. So I mean, this is also not like, it's not necessarily true that mine was wrong. I mean, it's not, I mean, there may be more than one reasonable instances of a given type class. So I think it's debatable whether it should be 3.4.10 or 10.4.3. But in any case, we can automatically get this instance. And now we also have a functor instance. So for example, we could apply function to, I mean, for example, square again. I mean, it doesn't make sense, or double. I mean, I could do 2 times fmap my example chain. And now instead of 3, 4, 10, I have 6, 8, 20 as the values for the blocks, for the transactions. Right, so that's functor and foldable. Are there any questions to that? So we'll see many examples of those type classes. They are all over the place in Haskell. Okay, then the last topic for this lecture. Tree, okay. I mean, did that. I mean, because tree is now an instance of foldable, we can, of course, also do stuff like sum. So, I mean, our example tree was this, and now we can, for example, do sum tree. And we get the sum of all the leaf values for free without writing a line of code, basically. So just by deriving foldable, we have that for free. Okay. Right, and the last topic for today is the thing we did for fold R. We started from the standard design pattern for lists, which follows from the way lists are defined, the 2 constructors. We abstracted away the standard design pattern. So instead of always using that explicitly, I mean, we had several examples, filter, map, concat, and so on. And instead of always doing this explicit standard design pattern, we abstracted that away and ended up with this function fold R. But there's nothing special about lists in that regard. I mean, lists are special in Haskell, they have special syntactic support. But as far, I mean, if you look at them as just a data type, an algebraic data type with constructors, there's nothing special about lists. So one can do exactly the same for other algebraic data types. And this relationship, I mean, this fold R for lists is called lists kata morphism. So that, I forgot what kata means. Andres knows, of course. But morphism is, I mean, like fancy word for function. And kata is some Greek, whatever. But that's a term. So each algebraic data type comes with its own kata morphism. In the case of lists, it's fold right. And so the last topic of today is to do this for some of the other types we looked at yesterday. So the easiest was bool. And there the standard design pattern just was that we need 2 equations, one for the true case, one for the fold case. So we have 2 basically blanks where we must fill in something. And so if we follow the same process that we did for lists, So we just give these two things names. So in this case, then prime and else prime. Then again, it wouldn't compile because the names are not defined. So we add them as parameters. And then it turns out, because they are results of our computation, they must both be of type R. And so this would be the katamorphism for Booleans. So that, like, fold R is for lists, this thing would be for Booleans. So intuitively, you give a function from Booleans by just specifying, two values, and if the Boolean is true, you pick the first one. If the Boolean is false, you pick the second one. And there, for fold R, we have its own name, fold R. For Booleans, this thing doesn't have a name, because if you reorder a bit, then it's basically just if then else. So this Boolean goes here, and the first R goes there, and the second R goes there. So if then else is the katamorphism for Booleans. So it basically abstracts away the standard design pattern for Booleans. So in the same way as we can write most list functions, or all list functions where we use the standard design pattern, shorter and compacter with fold R, we can write all functions on Booleans where we use the standard design pattern by using if then else. So as an example, yesterday we had this logical disjunction. Let me just, so that I don't have to hide anything, use 3 vertical bars. And we use the standard pattern. So we said the first one is true, we don't care about the second one, it's just true. And if the first one is false, then we return the second one. And now we could equivalently write that as x, y. Let me just comment this. Using if then else now. If x, then true, else y. This is probably, now it tells me I should just use logical, but right? So this is an example how, instead of explicitly using the standard design pattern, one could use if then else. Right. So that's Booleans. Then we looked at maybe. So maybe also has 2 constructors. So we always had 2 equations when we used the standard design pattern on maybes, nothing and just. And the just, of course, can use the x. So we have these 2 blanks where we must fill in our business logic. So we must have a value for the nothing type, and we must have a value for the just type case. But this value here can depend on the x, of course. So again, introducing names for these dots. So, and suggestively calling the one for the nothing case nothing, and the one for the just as a function of x, and then introducing them as new parameters to our function, and then figuring out the types, or letting the compiler figure out the types. We reach this function, and this is the katamorphism for maybe. And that does have a name again, and that's called maybe with a lowercase m. So that's in the standard libraries, which means everything that we wrote by hand using the standard design pattern for maybe, one can also write shorter and compacter using this little maybe. So as an example, maybe I did this map maybe just now, following the standard design pattern, and I could do this shorter and compacter with maybe. So map maybe f is maybe. So in the nothing case, it's nothing. And in the just case, it's so a function. So it's f. Just f. So let's do it slowly. So now there must be a function that gets this a. It must tell me what I want to return in this case. In this case, I want to return just fa. So I could write that more compact and to practice the dot like so. Yeah, and now it tells me that's just fmap. But, okay, so I made it right, did it right at least. Okay, so this would be an example of that. So, and is there another example? Okay, for trees. So obviously, because tree is our own type, that's not from the standard libraries, there is nothing in the standard libraries that has a name already. But for these common types, like maybe and so on, there are functions normally already defined. So let's do the same thing for trees. Maybe I can do that explicitly again. So what's our standard design pattern for trees? So fun, and we have some tree. So fun is from tree A to R. So we have two cases, leaf and node. So if it's a leaf, we must decide what, sorry, whatever that is. And if it's a node with a left and a right child, then we can recursively apply function to left and apply function to right and somehow use those two values to get our result. So again, so I have like two things that I must fill in. So this here is, I can call that leaf. That's a function, or leaf A. And here, let's call it small node, which can depend on the function applied to L and the function applied to R. Right, and now again, of course, leaf and node are not in scope. So let's add them. And add them as parameters. And I'm actually, oh yeah, okay. And here I must then add them as well. And now that doesn't compile because of this. What's now? Okay. And now it all, but let me just, okay, this go thing, what that, so I can, because leaf, I mean the same trick that we did there, so I can do, sorry, fun leaf node equals go, where, okay, go leaf R is leaf R, and go node go left, go right. That should compile again, and now I can use the compiler to give me the signature. And so we wanted this to be A, so each T1 I renamed to A, and the T2 is the result type, so let's call it R again. Then it looks a bit friendlier. Right, and this would be our catamorphism for trees, so that has no standard name. So I can, for example, call it tree cutter or whatever. And now functions that we implemented using this, for example, flatten, we can now implement with tree cutter. Is that here somewhere? Did I do that today? Sorry. No, I haven't. Flatten is not here yet, so I can immediately do that. So flatten takes a tree and flattens it. I mean, we don't have to. We saw we can just use toList. But if we didn't have the foldable instance, for example, so now using this cutter, so the first argument tells me how to deal with leaves, and the second argument tells me if I know the result for the left child and the right child, how can I combine the two to get the result for the whole tree. So if I have a leaf, to flatten it is the singleton list. And if I have the result of the left and the right child, I just concatenate them. So I can shorten that to this. And I could shorten this as well, but I don't. And now, what did I do now? Pass error. Oh, sorry. Tree cutter, I must. Yeah. Right, and here, okay, okay, that's maybe a bit weird. Right, and we can try it out. And flatten our tree again. Which I call tree and not tree 1, and we get the 749 again. Ugh. So I mean, this is, yeah, this is maybe more of, I mean, the fold R is used all over the place, maybe it's used all over the place, if then else is used a lot. As for other types with their cut, I think it's more normal to not do this and do it explicitly with the design pattern. This is more of theoretical interest maybe. And it's actually interesting. So there's a very close correspondence between algebraic data types and their katamorphisms. So each algebraic data type has a katamorphism. So following this process, I could do that for every algebraic data type. And interestingly, reversely, I can also go the other way around. So if I basically have the katamorphism, there's a way to define the data type with that. I always forget what it's called. There are two, it doesn't matter. Maybe we will have an exercise for that. So basically for each katamorphism, I mean, you can use the katamorphism to reconstruct the original data type. So there's like a one-to-one correspondence between them. But as I said, that's in practice maybe not important. That's more theoretically, or if you are into category theory, because there are katamorphisms, and then it would make much more sense. Just, yeah. Okay, so that's basically, so we have that for trees. Okay, and this is just a remark that I said. And like for common Haskell types, these katamorphisms often have a name. We saw now the example fold right and maybe and if then else. And for either, I think it's called either with lowercase e. And don't know if there are other prominent ones, but those pairs, it also has a name. Some forgot, but yeah. Right. So all these, yeah, there's this. Which, I mean, maybe, it depends, of course, on whether you are into math and into category theory. But for people that are, it may help to, maybe you wonder why did somebody come up with this maybe function, for example. So it can help to understand that this is all an incarnation of the same idea, this katamorphism idea, and that it's natural to have that function. Anyway, but for the time being, you can just try to use it, use fold I and maybe, and then just do this standard design pattern. And it's also, again, a matter of taste or style, whether the one is better than the other. Sometimes for easy things, it's better to use fold I, and maybe for more complicated functions, it may be clearer to do it explicitly. Are there any questions to this? I think we still do have time to do the... How much time do we still have?
Yeah, we have time.
We have time?
Not even 6 yet.
Yeah, because the next lecture is very short and we would like to do it today, that we don't have to do it tomorrow. It's only about tooling and packaging, so it's like intellectually you can relax. It's and let's do this quickly,
Yeah.
then we have that out of.
Also might help with like setup and stuff.
Yes. Right. I think so. That was this lecture. The next one, packaging and tools. Yeah. Fine, it's the last. Right. I mean, as I already mentioned in the very beginning, so Haskell programs are organized into modules, and modules are in one-to-one correspondence with files. So you can't have more than one module in a file, and they can be hierarchical, following the file hierarchy. So, so for example, data.list will be, and the names must also match. So the file name of a module, like, I mean, in my example here, sorry. I mean, this one, for example, that we use today, I called the module higher order functions, and if you look in the tree, the file is also called higher order functions.hs. And if I wanted to use hierarchical modules, then the folder names must also match. So here in this example, so there's this data.list module in the standard libraries. So that will be in a folder called data, and there will be a file called list.hs. So it's very simple. Or this control concurrent async, there will be a folder control that will contain a folder concurrent, which will contain a file called async.hs. So that's how file system and modules correspond to each other. Okay, that's I just said. So directories mapped. And right, we won't talk, I mean, we will talk about I/O tomorrow, how to do actual executables. But if you have an executable, then you must have a module called main. And that must contain a function called main, but we'll get into that tomorrow. So that's modules. And module header, I mean, we already have one here. So first it says module name, where optionally, we come to that in a bit, you can explicitly say what will be exported from your model, so will be visible outside the models. If you don't have anything here between the module name and the where, then it will export all top level definitions. Everything that I defined here will be available if you import that module. And then come import, so you can import other modules. And there are various ways. So you import them by name, and you can optionally have parentheses behind it and explicitly say what from this module you import. So here I'm saying, for example, I want fold left prime from the data list module. I could also leave the parentheses, and then I would import everything from the data list module. Then I can also, as we saw, hide stuff. So this means import everything from the prelude, but hide the things I list here. This is not so common that you do that. It's more like now for lectures or so.
The other way around, usually.
Yes. And then there's a way we haven't seen yet. It's called qualified import. So alternatively, I don't know, for example, if I now do want to compare, I mean, if I want the data list fold L prime available, I could no, I have it available, but if I wanted, that's a bad example maybe. No, if I want to show you that, whatever, the prelude all, I also want to show you that, but I don't want it to clash with my all. Then I can also do a so-called qualified import. So that looks like this. I can do import qualified prelude, and then I can say, I mean, for example, all. And I think this is great now because the prelude is always
It's because you already have the prelude like available, so it thinks you don't need that.
Yeah, and maybe prelude is not good. Maybe let's take something else from data list. Map is also in the prelude, right? I can just do foldable, for example. Qualified data.foldable. Oh yeah, okay. Data.car, for example. I mean, I could do this. I mean, now it's complaining because I'm not using it. But now I could have another example here, whatever, foo from character to string. Foo C is to upper C C. And now it doesn't find this, even though it's in data character, and that's because I imported it qualified. So I must now qualify it with its full name, and now it accepts that. Alternatively, I can also provide an explicit list here. So I can say qualified, but anyway, I only want it to upper. This is less common that people do that. But what is more common is that you give a shorter name, because it's irritating to always write data.character, and sometimes, as we saw with this control concurrent async, it gets very long. You can choose a name for it. So I could do as C, for example, and then instead of data.character, I just write C dot to use this. And this is sometimes necessary. I mean, it depends. Often, I mean, normally I would say the default is to import unqualified, but explicitly specify what you want. That's also, I mean, it's of course, if you are lazy, it's quicker to just import everything, but then it's harder for somebody that reads your code to know where this comes from. I mean, typically Haskell has like lots of imports, like 20 or so, and then if there's something you don't know, you just see these 20 imports and you don't know where does this specific thing you don't know come from these 20 ones. If you explicitly list what you import from where, that's easier. So my formatter automatically basically always suggests that. I mean, then it gets much longer still because you have the list of all these things, but it's sort of clearer. Because, I mean, for example, Cardano, I mean, sometimes I need to find something in the node or so. And I mean, it's a nightmare if you don't know where that comes from, because then it comes from Ledger or whatever. I mean, it's very deeply nested from all sorts of packages and libraries. So if they didn't explicitly say where stuff comes from, it's really hard. Right, and as for qualified, so there are some prominent packages on Hackage where they basically on purpose clash with names from the prelude. Or for example, data list has a lot of clashes with something called data.map. And there, so basically if you want to use those libraries, you almost always have to import it qualified. So it depends, but I mean with experience you will also see that. So that's basically import statements, and yeah, I could, and these explicit exports, so I could do this. I mean, normally one should always have an explicit export, so it's only now in the course that I don't, but I never have a model that exports everything basically. And right now it wouldn't export anything, because I mean, now that I have this export list, it only exports what's in the list, and because there's nothing in the list, now it wouldn't export anything, and now it screams that I have all these definitions, but I'm not using them because I'm not exporting them, so nobody's using them. So I could, for example, now export this foo, and if I want to export more, for example, the chain type, I can, with commas. And there's now, if I do it like that, only the chain type would be exported, but not the constructors. If I want to export the constructors as well, I can do it like this. This would now also export genesis block and block. But I can also be more explicit and, for example, only export the block constructor. But I think, I mean, yeah, that depends. So this is what exports look like. So now if somebody imports my higher order functions module, he would only see the foo function and the chain type and nothing else. But except for the instances, instances are always exported. So sometimes you see indeed a module with an empty export list, and that's still not useless because there might be instances defined and they are then exported. Right, I think that's basically all about this. Okay, and these import statements, they must really be at the top. So it's the module, I mean, first the pragmas, then the module header, I mean the module name with the export list, and then the imports. Okay, I think I showed you examples of all of that. Well, why is this slide there? I'm a bit confused now. What's this?
We still need to define what we export on top.
Yeah, and why does it then have a definition of this? It's somehow weird. I think there's a mistake in the slides. Never mind that. Probably the slides are somehow mixed up. I mean, I did talk about qualified already. You can also rename when importing, but I think we never used that in the course. You can re-export imported modules. So I could do something like, I could say module data.character. No, I can't because it's, but .list, for example. And then everybody that imports my module would automatically also get everything that data.list exports. Right, and you can export and import type classes and instances. Yeah, but I mean, you don't have to remember all of that. I mean, you can figure that out, and it's relatively logical and straightforward. Okay, now packages. So we have modules, and modules are organized into packages. And they are not really a thing of the language. I mean, modules are part of Haskell, but packages are part of the infrastructure, GHC. And we somehow, of course, if we want to use packages from Hackage or packages that we have lying around locally, then we have to tell the compiler which packages we depend on. And I'll show you in a second how. But I already mentioned on the first day, I think, that there's this one package base that's bundled with the compiler. So that's, you don't have to, I mean, that's basically always available. If you have GHC, the compiler, you always have access to the base package. And incidentally, they are versioned, I mean, it's versioned, and the version of the base package depends on the version of GHC. So somehow they are linked. So a specific version of GHC only works with a specific version of base. And I always find that a bit weird. I mean, it's not obvious which goes to which. So I always Google it to find which base version I need. And as I said already, I mean, Prelude is part of base. We also saw the documentation yesterday briefly in base. There's a module called Prelude, and that is, I mean, implicitly always imported. So like maps and, I mean, lists, no, not maps, lists and maybe and the most common stuff you always have available without importing anything. That's because the Prelude, everything that's in the Prelude is automatically available. But you can switch that off. There's an extension called no implicit Prelude, and then you have bare bone Haskell, nothing predefined. which incidentally is used by Plutus, because Plutus has their own prelude. So if you write Plutus code, then you normally use this extension. Right, and Hackage I already showed you yesterday in the browser, this Hackage package repository. And I said that lots of useful stuff is there. From professional things to hobby projects and research projects, and yeah, there's lots of information there. Although, to be fair, one of the biggest complaints to Haskell is always that documentation is really bad. Because I mean, the joke is always that the idea of a Haskell programmer to provide documentation is to cite a research paper, and I mean that's often the case. That's true. But it's getting better in recent years. And there are some library authors that are really exemplary in their documentation, like Gabriela Gonzalez. I mean, they come with tutorials and like modules that are just there to learn, and so some are really good. But you also get this classic one where it's just a one-line documentation, C, and then some computer science paper. Okay, and the package manager and the tool that also like organizes everything, and that is called Cabal. So yeah, and that has like two meanings. It's both basically I don't know what that's like the package.json file for Node. We have in Hackage we have a Cabal file that basically says what is where and what dependencies you have. And then Cabal is also the tool to use. I use Cabal REPL, for example, to open the GHCI, and you use Cabal build to build your project, Cabal test to run tests, and so on. So Cabal is like the main tool. The compiler GHC, you can just invoke it directly, but I've never, just to try it out, but you never do that. You always use Cabal, and Cabal then calls GHC. And we can just do this now with Cabal init, maybe? So let's create a package. Let me just concentrate. So I do this. So this is now, yeah, let's do it here. So I am in this examples Haskell folder where we have our examples. So let's create a new one.
Can you clear the screen?
Yes. Right. It's a bit unfortunate that my prompt is so long, right? But there is no way to about.
I have to change the configuration.
Yeah. Anyway.
Want to use mine?
Nah, I think it's fine. Make it even longer so it's short again. Right. So there, Cabal, and Cabal, this is very intimidating if you ask for help. It's like 500 pages. Not really, but it has a lot of flags. But one of the things it has is Cabal init to set up a new package. And that has this interactive flag. So let's just try that.
It's by default.
Okay. Do I have to create a directory myself? Or?
Yes.
Okay, so I create a directory. Let's call it 06. What was it? Packaging and tooling? Just a second. I'm a bit. Packaging and tools. Okay, so now I created a fresh directory. It's empty. Now I can do Cabal init, and now it will ask me questions.
Which version do you have?
No, it doesn't ask me anything.
Maybe because you have a different version, not the last one.
Okay, I can do the -i.
Yeah.
Okay, so whatever. Should I generate a simple project with sensible defaults? Let's say no, because otherwise that's the only question it asks, I think. So now it gives me three options: an executable, a library, or a library and an executable. So because we talk about I/O and executables tomorrow, let's go with the second option now. So I pick 2. Okay, what now? Please choose version of the Cabal specification. No idea, but let's...
This is the structure of the Cabal file. Has like names and like specific names in specific options, and depending on the version, you have like newer or updated versions.
So I can use...
Usually it should be the last one.
Okay, so the default would be 4, but I pick 5.
Yeah. And
Because that's the default. If I just push enter, it would pick that.
you will get more options because your Cabal is...
Yeah, mine is a bit, I should have updated. But
Yeah, and you have 3.4 the last version.
well, maybe, should I now use GHC up to change it?
Or maybe you can spin up the development environment.
Right, but then yeah, I can do that.
If you use 3, I don't think it changes like at all.
Okay, hang on. Let's do this. Let me close my editor. And this is what I don't understand. That's what I said earlier. I broke something because now there is nothing in the Explorer.
But do you have the environment at least? Maybe you can...
I'm sorry? Do I have?
Can you try running the terminal? Like opening the terminal?
Yeah, sure.
And maybe you can do just Cabal init.
Yeah, but where will that end up?
No idea. Because you should have like the default.
Yeah, so something is wrong there.
Yeah.
But I think if I do it in the other, this is the teacher repo. Let me do it in your repo. That should be fine. Sorry, let's do this. I think that will work. Not really.
Use your installations.
Okay, fine. So if you try it, then it will be a bit different because you have a newer version than the one installed on my machine.
The flags are the same.
Yes, but just principle of the matter. So let me do this again. I just want to see. Sorry, I have to.
You need to go.
Yeah. Okay, so it already started doing something. So remove.
Yeah, but for the fall event.
Yeah.
Start.
Okay. Okay, let's start. Do this again. Cabal init -I. No, not defaults. Library 5. Package name. I mean, I always called it without the 0 thing. Tools. Yeah, that's fine. Default version. Now I can choose a license. For example, none. Of 5. Yes, 5 is good. Author name is already, it gets that from some sort of Git. Email. What do I know? Now I could pick, I mean in Hackage there are categories where you can easier find interesting packages, so I could, I don't know, is there anything that fits? No, not really. Language, what? Testing, yeah, whatever. 6, it doesn't matter. I could also say none, but...
If you're not going to push it to Hackage, no.
Yeah, it doesn't matter. And now I can choose what the library, the source directory, where like the root folder of my source code is. I always use source. I've never used one of the others. Should I generate a test suite? Let's say no, because we talk about testing next week.
Yeah.
Which version of Haskell? So see, that's why I never saw it, because.
Right. Yeah.
So let's pick Haskell 2010. I mean,
You have another option. You will have another option, Haskell 2020, that there is called JC 2021. But for now, just use 2010, because then every extra flag we need, we are going to explicitly put it there, so you know what's going on, and you can just Google like what each flag does, just so there's no like new stuff popping out of nowhere.
Right. Add informative comments to each field in a command file. I mean, normally I don't, but let's do this. Okay, and now it generated a bunch of stuff. In particular, it generated the cabal file. So I could now do code dot. Let's see. Okay, so license is just the MIT license because I specified MIT. Changelog I've also never used in my life, but I always delete that. I shouldn't. Okay, and this is now very verbose. I mean, normally it looks smaller, but now because I said yes to add informative comments, so that you can see. So this looks now worse than it is. So I mean, here's this cabal version, the name of the package, the version, synopsis. You could give an explanation of what this is about. Homepage, license MIT, license file is now specified. Author, maintainer, category. This is for stuff like the license, or no, not the license, but like readmes or so that are not Haskell files. And this is now the interesting part.
I think maybe we should delete this part, these comments, right?
Yes.
It looks
I probably should have said no.
way more complicated.
Yeah, I should have said no, but maybe if you try it, it's informative to. So let me. So you see, I could also give. What was it? A copyright note and so on. Okay, let me make it a bit shorter. Then it looks far less intimidating. Yes, there's one thing. Right. Okay. So, yeah. So this is basically it. So these are these general metadata stuff, and the interesting part is here with, I mean, your modules. So there should be now a source directory that has this mylib.hs. So I have one module, and this is what packages I depend on. And you always depend on base, but optionally you can depend on other packages from Hackage. And one thing that you always should do is it options GHG or GHG options? I never, because I think the pragma is the other way around. So you can provide options to the compiler, and the one that you should always do is to activate all warnings. So that I always add. You can also, for executables, add optimization and do all sorts of stuff, but this is the most important one. Otherwise, you don't get many of the warnings we now saw all the time.
And in yours, like when you use Cabal with the new version, it already provides that flag. So commonly used that it's already there.
Ah, okay, cool. Right, and now maybe to show this hierarchical stuff, we had on day 1 we had this table example, or day 2? Day 2. Let me try to somehow find this. Sorry. There was this CD, blah, blah, this day 2. No, day 2, but it was data types and functions, right? So copy 3. Sorry, just have to concentrate. I just copied this file from day 2 here. And what I want to do is that we somebody defined this table type. Right. So I wanted to keep this. And let's call it data.table. So this, remember we talked about new types and how you would hide and so on, and we couldn't really demonstrate that because we hadn't talked about these things yet. So now we can demonstrate. So I want this table type we defined, I want to have that in a module in this new library I'm now doing. I want this library to be called data.table, which means I need a folder that's called data and move it there. So let's create a folder here. They're called data. And I move this thing into that folder and I rename it, I rename the file to table. Okay, so far so good. I mean, of course, right. And in the Cabal file, now I have two modules. I have this mylib and I have now this data.table. So I must add that here. I always sort them alphabetically, but it doesn't matter how you sort them. And do I need a comma or not?
Yeah.
Yeah. Because for some things you don't. But anyway, right. So this is now, I mean, there's also a way to not expose this. I mean, this means that now everybody that uses your package can import this module data.table. There's also a way that it's only used internally and other people can't. But maybe for now this is fine to just use this exposed module. Now let me just clean up this thing a bit. Because we did all sorts of things. So I did this new type. And then we had our interface, empty, insert, delete, lookup, and then we went to another example. And now it probably complains because lookup conflicts, yeah, to prelude lookup. So let's hide this again. And hiding lookup. Okay, now I can choose what to export. Now we make use of this export list, and Robertino and I try to explain that if you don't export the implementation of the type and just the interface, then later you are free to change it. So let's just export table, but not the constructor of table. So people can only construct tables by using the interface. And then this interface we had, so empty, was it insert, delete, and lookup. I think that should be it. So now this is a module that we define, data.table. It only exports the table type, but not the constructor. So you can't directly construct new tables or pattern mention it. But you can work with tables with this interface we implemented, empty, insert, delete, and lookup. And now I can in the mylib. Okay, let's delete this some func thing that was just put there by Cabal init. So now I can import my data.table. And now I would get, again, a clash with this lookup. So this might be a good case where one would do it qualified. As T, for example, for table. And now I can work with this here. So I can, for example, say table, what I don't know. Oh yeah, we had these programming languages and whether they're good or bad. So it was a table. Oh yeah, and because I imported it qualified, I now have to say t.table. And in that case, actually what many people do is they have another import, non-qualified, but just for the type. So the type table I can use unqualified, but operations I now have to qualify. And let's say table is t insert Haskell true. insert Java false, insert Python false, insert Bluetooth true, empty. Right. So this demonstrates that I can now use, I mean, how now I have defined the, oh yeah, and then maybe I should show with Cabal, now I can build it. Just sorry, have to wait a second until, for some reason it always takes a moment. Okay, there we go. So for example, I can do Cabal build. And that will now hopefully, without warning, okay, it built it, so this is now fine. So I set up a new package and with two modules, mylib and this data.table. And now I should be, if I do Cabal REPL, I'm in the REPL, so now I'm in the data.table module, but I can load the mylib module and can ask for table, and so that worked. And now maybe the last thing I want to show you is how you would import something from Hackage. So there is a module with a very similar interface, but much more efficient, also key value pairs, but efficient implementation. And that's a very common package. Almost every Haskell project on this planet uses that. It's called containers. So, I mean, you could look on Hackage, containers, make it bigger now, containers, Hackage. Right, so in particular that has a data.map type, which has a very similar interface to our table type. So if I wanted to use this in this project now, I could go back to my Cabal file, and here under build depends, where right now it only depends on base, sorry, I can add containers.
How do you know that it's named container?
I just wanted to get to that. This is, I mean, the name is here. So on Hackage, this is the name. And if you are somewhere in the documentation, then it's here on top, the name of the package. And you could specify a version, but you don't have to in Cabal. So you can also, I mean, then Cabal figures out a version that fits. So if you see here, I mean, for example, here it says, I mean, all these versions exist. And it also shows the dependencies. So containers also depends on base and on other stuff. So, and Cabal, one of the things Cabal does is it tries to find versions of all your dependencies and transitive dependencies so that everything fits together. Okay, so I just add containers here. I think in the, no, don't want to. I think if you change something in the Cabal file, it's a good idea to reload in Visual Studio. Sometimes HLS doesn't catch that. But now I have the containers as a dependency. And now I can use that, for example, in my lib. So I can do this, what I did here for table, I can now also do for this map type. Data map. Qualified data map as M, for example. And now I could, it has a very similar interface, as I said. So in particular, it has insert and empty with the same signatures. I do have to restart the REPL because I changed the dependencies, otherwise it wouldn't catch that. Now I can go to my lib and now I can ask for my table prime, and that also worked now. And it looks sort of similar. But I mean, it's now using this package, this efficient package package. Yeah, and that's basically all you, I think, need to know to get started. Let's just check the slides whether there was anything that I now didn't mention. Demo. Okay, yeah, that was that. Right. So yeah, showed you how to set up a. I mean, but to be honest, I very rarely use this Cabal init. I always copy an existing package and edit stuff. But of course, that's up to you. Right. So now you see how to use like modules and import, export. And the details, of course, you can always look up in the documentation. It's mostly important to know that these things exist and are possible.
Should we show it in the Cabal manual?
We can. Where's the Cabal menu? Okay. So there's a Cabal user guide, which has 1,000 pages. No, I don't know.
Yeah, kind of.
It's long.
No, but with introduction, that's good enough. There's this getting started and introduction.
Yeah.
That is like 90% of things we need to
Yes.
know. Or 100 maybe.
So I mean, they can look up the details about syntax in the Cabal file and so on. But I normally really just take an existing one and edit it lightly. But sometimes, yeah, you need to know something and then you can check it there. Right. So yeah, there's lots of information on Cabal. And so I mean, sorry, oh yeah, I did compile already. So maybe I should have mentioned that when I, in this case, for example, it didn't, it seems I had containers for this GHG version already on my system, because if not, then it would say something. I mean, when you do Cabal build or Cabal REPL, so it has to get this dependency from Hackage. So then it would say something, the following, here it says, the following will be built, and first it would figure out the dependencies. I mean, this is now very simple because it only has base and containers. But something like Plutus has literally hundreds of dependencies. And then if you run it for the first time, you get a very, very long list of stuff that has to be built. And then it downloads it from Hackage and builds it and installs it, and it can take a long time. But once you have done that once, then, I mean, it's cached on your system. So if you don't change the dependencies or upgrade to a new version, then next time it's fast. So Cabal only rebuilds what it needs to rebuild. And in my case, because containers is so common, I obviously already had this version installed on my machine, and therefore I didn't need to do this now. So it was very fast. But it can take longer if you have like new dependencies that you pull in.
And in the IO class, we will see like the executable part of things, right?
Mm-hmm.
Because now it's just library, but then we want to actually have like a runnable binary.
Mm-hmm.
Yeah, but we need to talk about IO.
Yes, but that we do tomorrow. So,
Tomorrow.
I mean, there's this. I mean, I told you that Haskell was designed by a committee, and there are like prominent members. I mean, one was Phil Wattler, for example, who works for IOG now, and there were actually several people that work for IOG. But anyway, but one is called Simon Peyton Jones, and he is like I mean, if there's anybody that's like the main Haskell person, it's him. His son is one of the creators of Plutus, actually, and he has this fame. I mean, he's very nice, Simon Peyton Jones, and writes very nice papers. So if you ever have a chance to read one of his papers, it's beautifully written, very easy to understand. And but there's this famous video where he says Haskell is useless, and what he means by that is that without I/O, I mean, what we have done so far, I mean, you can't run anything. I mean, you can inspect it in the REPL, but you can't have an effect on the world. You can't fire missiles or do internet requests or whatever. You can't interact with the outside world. So we'll get to that tomorrow, and then you can start firing missiles. Okay, then I think that's enough for today. Are there any questions? Yes?
So if I import maybe a module that's excluding something from Prelude, will it be excluded also where I'm importing it?
That's a good. No.
No.
This is only, I mean, if you don't explicitly in the export list export a module, then the stuff that some module you imports, that doesn't matter. I mean, you only see what that module explicitly exports.
Exactly. So, like, if the module exports something, like, again, something that was already in Prelude, you will have a crash with your own Prelude. But if it doesn't export something that you have in Prelude, you won't have, like, no crash.
So I'll also have to exclude it in my.
You don't need to exclude it again.
So that it doesn't clash, maybe.
Right. So if the owner of the library excludes something in the Prelude,
I should also exclude it in my Haskell.
you don't need to exclude that
Okay.
because you have a different Prelude. You have like your own Prelude. The owner of the library just like what you get from the library is only what it exported, not what it imported in the library.
Because look at this scenario, let's say I wanted to use this find his own carry method. Then I try to use carry in my Haskell file. Will it use my Prelude's version of his Preludes? Or is that?
No, it's the same.
If
I mean, if he depends on the Prelude and exports something from the Prelude,
the other person,
and you also depend on the Prelude, then there is no clash, I think.
right?
If there are different paths that import the same thing, then there is no clash.
Also, like, for example, when Lars imported twice the data.map, it's not actually imported twice. This is just to manage the namespace available for the developer. But then Cabal figures out a way to import only the needed source.
I mean, we can just try this. We have our table, and we could, for example, export something from the Prelude map, for example, map. And I think, I mean, I'm pretty sure that doesn't do any harm. I mean, it doesn't do anything. And if I now in my lib, so now I have like two ways of, I mean, two maps, but they are both the same. They both the one from, let's try this, foo, a list of ints, foo is map +1, 1 to 10. And that's perfectly fine. So, oh no, sorry. This is no. Of course, because I imported that qualified. But if even if I don't import it qualified, I mean, if I say import data table map, let's see what happens then. I think then I just get a warning. Right. It's redundant because so it's not an error. I mean, the point that's I think important to mention in Haskell. I mean, there can be lots of transitive dependencies. I mean, I now depend on containers, and containers depends on lots on other things, and they can depend on other things. And of course, you can have like cycles that you depend on two libraries, but they both depend on containers, for example. But it's always the same version. So each library you depend in your transitive dependencies is a fixed version. So if I depend on library A and B and they both depend on containers, they must depend on the same version of containers. So you can't have like different, depending on how you import something, have different paths. And that makes it of course more difficult to, I mean, for Cabal to figure out versions for everything so that everything fits together. But so it doesn't matter that now I have this map. I exported it from my table module and I implicitly have it because it's in the Prelude. So now I get a warning that I have it twice, but it's no error. I mean, it's the same map because it's both the one from Prelude. So it's fine. I mean, it doesn't matter.
It's extra code.
Yeah. Okay.
Other questions?
And that can be a real pain with a large project like Plutus, if you do some Plutus stuff, to get it to compile, I mean to get Cabal to find compatible versions, that can be a nightmare.
Yeah, that's because we have lots of things in GHC and in GitHub and stuff like that.
Yeah. Normally these days, I mean, when I started with Haskell, it was really painful to figure, I mean, because then it also had a global cache. So basically, if you had different projects in each project of your project, you basically had to use the same version of dependencies. But since, I don't know, 7 years, 10 years, Cabal is much better. So it has like these isolated sandboxes. So each of your projects is independent. So you can have one project that uses container version whatever, 1, 2, 3, and another one that uses a different container version. As long as it's different projects, then it's fine. So you can have now different, and that made life much easier. But for very complex Haskell projects like some Pluto stuff, it's still sometimes painful to get everything fit together. There are all sorts of tricks you can still do there's a so-called Cabal project file where you can these version bounds that, I say I want dependency so and so. There are ways to override that and say, okay, you want this, but you don't get it. Live with it, deal with it. So yeah, there are all sorts of ways. But normally for small projects, it should be simple. Okay, that's it for today. Thank you very much.